Welcome to this module of this course Computer Aided Power System Analysis. Up to the last lecture, we have derived the expressions of the elements of the Jacobian matrix. Earlier to that, we have also looked at that what is meant by the correction vector and also what is meant by this mismatch vector. So, now today we would be looking at the complete algorithm of the NRLF polar method as well as one small example for this. So, complete algorithm. So, in step 1, assume flat start. And we have already discussed what is meant by flat start when we also have generators in our system. Please do remember that we are considering a general system where we have got n bus, m generators, bus 1 is slack, bus 2 to m, PV and m plus 1 to n r p q. So, this is our convention. So, this for this where n and m can be of any value. So, for this we are going to rather discuss this complete algorithm. So, the first one is the assume flat start. Then what we do is then for I is equal to 2 to m, calculate q I and let us say also initialize k is equal to 1, k is equal to k's iteration count, k's iteration count and we set k is equal to 1, k is iteration count. So, then we calculate q I at kth iteration. So, the first iteration as j is equal to 1 to n V I k minus 1 V j k minus 1 y I j sin theta I k minus 1 minus theta j k minus 1 minus alpha I j. So, what we are doing for bus 2 to m, we are calculating that what is the reactive power generated by these generators. What is 2 to m? 2 to m is in our parlance that we are essentially calculating that what are the reactive power generated by each of these generator at this present iteration. And when we are calculating the reactive power generated at kth iteration, in this case k is equal to 1 when we start this kth iteration, at this point we have only have the knowledge of the all bus voltage and angle corresponding to the last iteration, that is basically corresponding to the k minus 1th iteration. So, then here in this expression in the last rather in this expression given at the right hand side, we would be always using the values corresponding to k minus 1th iteration. Then step 3, if q I k is less than equal to q I max and greater than equal to q I mean, then we say that V I k is equal to V I specified. we note the remark, it is for our own understanding. Remark, ith bus remains as PV bus. If else if Qik is greater than Qi max, then what will happen? We have already discussed when we were discussing the Gauss-Seidel load flow analysis. We have already discussed that if this calculated reactive power by the generators remain within the limits, remain within the corresponding limits of ith generator, so then in that case that ith generator remains as a PV bus. On the other hand, if this calculated reactive power crosses any of the limits, either maximum or minimum, so then in that case that particular bus voltage magnitude at the ith bus will not be maintained at the specified value, it will be changed, and that particular bus would be now treated as a PQ bus. Now, in that case what will happen now, because this calculated value of Qik, for example, here in this case if it is crossing Qi max, so then therefore physically this generator will not be able to supply this much of reactive power, it would be able to supply only a value equal to Qi max. So, then in that case, so then in this case this particular generator will act as a PQ bus, where the specified value of Q which is being injected by this generator would be equal to Qi max. So, then therefore, if Qik is greater than Qi max, we Qi specified would be equal to Qi max, and else if Qik is less than Qi mean, then Qi specified would be equal to Qi mean, because in this case less than means that if this generator is asked to absorb more than this Qi mean, so then obviously it would not be able to absorb more than this. So, then it would be only able to absorb a value equal to Qi mean. So, then in that case the specified value of the reactive power at the ith generator terminal would be equal to Qi mean. We again take a remark for our own convenience. The remark is, in these cases PV buses are switched to PQ buses. So, again this is a remark, this is for our own understanding, algorithm is only this. So, then what would be the next step? Now, here we need to understand one thing. Suppose bus I has violated the limit. So, then therefore, what will happen? That means that particular bus I has now been changed to PQ bus. When you say that this bus has now been changed to PQ bus, so then therefore, its voltage magnitude will not be maintained at Vi is equal to Vi specified, it would be something else which needs to be calculated. So, then therefore, for this particular bus, when ith bus is being changed from PV to PQ, one extra unknown is generated, that is basically the extra unknown is corresponding to its voltage magnitude. Now, because there is one extra unknown is being generated, so then therefore, we also need one extra equation to solve for this extra unknown along with the other equations. Now, from where we will get this extra equation? This extra equation we will get from this values of q I specified is equal to either q I max or q I min, right. So, then therefore, we write that, so it would be step 3, if there are L violations, L limit violations, L limit violations, we write of the generator reactive power limits where L would be less than m and greater than 1, greater than equal to 1, less than equal to m minus 1, because you see number of PV buses is equal to m minus 1. So, then where L would be either greater than equal to 1 or less than equal to 1, then there will be extra L unknowns. Now, what would be these extra unknowns? These extra unknowns are are the bus voltage magnitudes, we write in language to for better understanding, bus voltage magnitudes at all the buses where the limit violations take place. So, then therefore, to solve for these extra L unknowns, extra L equations are also available in terms of QISP at these buses. In fact, we should not actually write it as an algorithm step, we rather should write it as an remark. So, we write it as an remark, it is also a remark. So, now we come to step 3. In step 3, if there are L violations, then what would be the V vector? V vector is already V m plus 1, V m plus 2 to V n, and let us say this is V A, V B up to say V small p t, where A B are the buses at which violations take place. Further, what is the vector q? Q vector also changes. What is that q vector? It becomes q m plus 1, q m plus 2 to q n, and then q a, q b, q p. So, then therefore, dimension of V vector increases from n minus m, earlier it was n minus m cross 1, to n minus m plus L cross 1. Similarly, dimension of q vector also increases from n minus m cross 1 to n minus m plus L cross 1. Now, what are the Jacobian elements? So, then what would be the Jacobian? So, then dimensions of the Jacobian submatrices. J1 is, that is del p by del theta. It would be no change, it would be still n minus 1 cross n minus 1, because the dimension of vector p or vector theta has not changed. What happens to J2? That is del p by del v. What happens to this? It happens, it becomes n minus 1 cross n minus m plus L, because this vector v dimension has now changed from n minus m to n minus m plus L. What happens to J3? That is del q by del theta. Del q has now increased. Now, q vector has now increased from, or rather the dimension of q vector has now increased from n minus m to n minus m plus L. So, it becomes n minus m plus L cross n minus 1, and what happens to J4? That is del q by del v, that becomes n minus m plus L cross n minus m plus L. So, then therefore, overall Jacobian, so then overall dimension of the Jacobian matrix increases from 2n minus m minus 1 cross 2n minus m minus 1 to 2n minus m plus L minus 1 cross 2n minus m plus L minus 1. So, the overall Jacobian matrix. So, what happens to this delta x vector? Delta x, what is this delta x vector? Delta x vector is delta theta 2 to delta theta n, and then it would be delta v m plus 1 up to delta v n, then delta v a up to delta v p. So, this becomes this. So, its dimension also becomes 2n minus m plus L minus 1 cross 1. What about delta m vector? That is the mismatch vector. It becomes delta p 2, it becomes delta p n, then delta q m plus 1, delta q m plus 2, delta q n, delta q a, q p transpose. This is also 2n minus m plus L minus 1 cross 1. Right. So, then after that what we do? So, once we do this, so once we do everything is done. Now, what we do is we calculate this vector delta m as defined above. So, we calculate all these elements delta m, and let us that this delta m vector is defined as, let us say, delta m 1, delta m 2 up to delta m 2n minus m plus L minus 1. Please note that this m and this m, they are not the same. This m, capital M, denotes the mismatch vector, or rather the basically the element of the mismatch vector, and this m which is in the subscript, they denote the number of generators. So, we just write it. So, this is the number of generator in the system, and this m, all these big m's, these are the element of the mismatch vector. So, after that what we do? We calculate EI as EI is equal to delta mi for all I is equal to 1 to 2n minus m plus L minus 1. What we do is we simply take the absolute value of all them. We just simply take the absolute value of this, absolute value of this, absolute value of this. We just compute the absolute value of all the elements of the mismatch vector. We should write calculate. Then we calculate, in fact, everywhere it should be EIK, it should be EIK In fact, everywhere it should be actually subscript k, subscript k, subscript k, 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 k. Everywhere there should be subscript k, because we are doing it at the kth iteration, we have missed it. K, all are k, here also it would be k. This is also k, 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 k. These are all corresponding to kth iteration. These are the unknowns which we wish to solve for. These are the all unknowns. These are the knowns which we would be using. So, these are all corresponding to k. So, then what we will do, if then calculate error at is as max EIK if error is less than some epsilon, stop, else go to step 9. What do we do in step 9? We simply evaluate the Jacobian matrix at kth iteration, evaluate Jk using V vector k minus 1 and theta vector k minus 1. So, we evaluate Jk by using this V and theta vector, which is available in the last iteration, and then we calculate delta x vector at kth iteration as inverse of So, we take the inverse of this matrix. Remember, it is a matrix and it is a square matrix, and so we take the inverse of this and we multiply this, we get this, and then we update x k is equal to x k minus 1 plus delta x k. And we have already defined what is this matrix delta x k, and x k would be theta 2 etc. K, update k is equal to k plus 1 and go to step, which step we will go back? Step 2. So, this is the complete algorithm. It is very simple algorithm, not really very much complicated. Only thing is that at each and every iteration, at the initial stage of this iteration, we will first calculate that how many reactive power violations have taken place. So, accordingly we will update the unknown vector, that is delta x, we will also update our mismatch vector, that is delta m, and we will also update our Jacobian matrix, and we will also change their dimensions suitably, and after that we will cross check that whether any of this mismatch has, or rather whether all of these mismatches have gone down below certain threshold value or not. If they have gone down below certain threshold value, so then we say that our algorithm has converged, otherwise we simply update, after that we simply calculate the correction vector, update this voltage as well as angle, and then go back and then reiterate. So, with this we will now look at a simple example. Simple example is that we again look at that same 5 bus system, and in that 5 bus system, if you do remember, we had 3 generators, and bus 1 generator is considered to be the slack bus, and bus 2 and 3 are considered to be the PV bus. So, then therefore, in this case n is equal to 5, that is basically the number of bus is 5, and m, that is the number of generator, is 3. So, then therefore, J1 is n1, J1 is n minus 1 cross n minus 1. So, it is 4 cross 4. J2 is n minus 1 cross n minus m. So, it is 4 cross 2. Similarly, J3 is 2 cross 4 and J4 is 2 cross 2. And then we, without generator Q limit, that is, we have initially considered that all these minimum and maximum values of this generator is pretty high. For example, for all these generators, this minimum value has been taken as minus 500 MVAr, that is, it can absorb up to 500 MVAr, and the maximum value has been taken as 500 MVAr, that is, it can generate up to 500 MVAr. So, because we have taken a very large value of this limit, so then it is virtually there is no generator limit. So, then without any generator limit, we iterate this and we find out this result. This result is identically the same as we have observed in the case of Gauss seidel load flow. If we just compare it, you will find it. Here again this bus voltage magnitude at bus 3, all these bus voltages are maintained at 1, and iteration is only 4. On the other hand, in the case of Gauss seidel load flow, the number of iteration was much more. It was, I think it was something like 69. So, let us look at the comparison of convergence characteristics. So, if you look at the convergence characteristic with GSLF convergence characteristics very slow, it takes roughly about 69 iterations. On the other hand, in the case of NRLF, this convergence characteristics very fast, it hardly takes 4 iterations. Now, please remember, in this case we have taken this threshold value as 10 to the power minus 12. So, here also we have taken 10 to the power minus 12, and for NRLF also we have taken 10 to the power minus 12. So, with this GSLF takes 69 iterations, and with this NRLF takes 4 iterations. So, NRLF takes much less number of iterations as compared to GSLF. When I do the same exercise by applying this generator Q limit, this generator Q limit is the same as we have considered for this GSLF. Then we find out this result. Again, this result is also same as we have obtained for this GSLF. And here also this particular bus voltage magnitude is not now remaining at 1.0 per unit, because here this because now here what will happen for bus 3, we have now reduced this maximum reactive power generation limit as 50 MVAr, but as we have seen in the case of GSLF, this particular generator needs to supply more than 65 MVAr to maintain its voltage at 1.0 per unit, but because its generator production limit has been clipped at 50 MVAr, so it can only supply up to 50 MVAr. So, as a result its voltage has gone down. So, earlier without any generator Q limit it was maintained at 1.0 per unit, but now it is maintained at 0.9825, and rest of the other things have been, and the other results are identically the same. Again this total iteration has just increased by 5. So, 4 and 5 there is not much of a difference. So, even with generator Q limit, the number of iterations taken by NRLF is much less than what is taken by GSLF. So, in this lecture we have looked into the complete algorithm of the NRLF polar, considering all these practical aspects, that is the number of generators as well as their generator Q limits. And we have also looked into one small example, that is the same 5 bus system example, and we have seen that this results obtained by GSLF and NRLF are identically the same, although the number of iterations taken by this NRLF are much less than that taken by GSLF load flow algorithm. So, from the next lecture onwards, we will be considering some other algorithms. Thank you.